The TEMP tutorial presents the step-by-step procedures involved in creating a simple geothermal problem. Here is a schematic diagram of the problem to be solved. The objective is to compute the depth of the frozen zone that will develop beneath the ice surface after the temperature of the ice has been maintained at -5 degrees Celsius for a period of 8 months. Outside the ice surface, the floor of the building is assumed to be insulated so that no heat can cross to this part of the floor. Prior to placing the ice, the in situ ground temperature is at a steady-state condition of 3 degrees Celsius at the ground surface and 3.1 degrees at a depth of 4 meters. The material properties for the ground and the relationships between temperature and thermal conductivity and unfrozen water content can be found in the GeoStudio tutorials book. Once GeoStudio has been opened, a new TEMP analysis can be created from the Start page by selecting an analysis, creating a new project, or using the File drop-down menu. The first time you start working with TEMP, it's helpful to learn what different toolbars exist. Many of the drop-down commands are also available as individual icons on the many different toolbars. You can familiarize yourself with the toolbars by toggling them on and off, ensuring that they are all visible before you start the analysis. When developing a numerical model, the first step is usually to set the working area, which defines the size of the space available for defining the problem. The working area may be smaller, equal, or greater than the printer page. The next step is to set the units and scale. The units for this particular simulation need to be set for length units as meters, time units as days, temperature units as degrees Celsius, and heat energy units as kilojoules. The scale should be set such that the minimum and maximum extents in temp match those required for the analysis. You can define the X and Y minimum and maximum extents to get an idea of an appropriate scale, and then fine-tune the scale to have a 1-to-1 aspect ratio. A background grid of points will help you define the problem. These points can be snapped to when creating the problem geometry. The problem definition data has to be saved to a file. The data may be saved at any time during a problem definition session, and it's a good idea to save the data frequently, and all TEMP files have a GSZ file name extension. Click the Zoom page icon to view the entire working area. It's often helpful to sketch an axis, which will then help you to define the geometry. The axis is drawn by moving the cursor to the bottom left corner of the axis, clicking the left mouse button, and then stretching the axis outward until the necessary size has been achieved. The number of increments can then be adjusted using the Set Axis drop-down menu. Before creating the finite element mesh, it's convenient to first prepare a sketch of the problem. Select Sketch Lines from the Draw menu, and use the cursor like a pencil, clicking the left mouse button to create a series of lines that outline the problem features. Click the right mouse button to exit Sketch Lines mode, and then use either the pull-down menu or the Sketch Lines icon to complete your sketch of the problem. If you sketch a line in the wrong position, you can use the Modify pull-down menu and select Objects. The incorrect sketch lines can then be selected and deleted or adjusted as required. Once the problem has been sketched, some information about the analysis to be conducted needs to be defined. Choose Analysis Settings from the Key-In menu. The following dialog box will appear. Any appropriate text can be typed under the Project ID tab. Click on the Type tab and select the Transient Analysis option. Click on the Control tab and make sure the analysis view is two-dimensional. Click on the Convergence tab. Set the number of iterations equal to 50 with a convergence tolerance of 0.1% and a rate of 9 Gauss regions per iteration for the development of the phase change region. A transient analysis means that you are interested in what happens with time. Click on the Time tab to define the time steps. This problem will be analyzed by using small time steps at first, then increasing the time steps to a maximum increment of 100 days. The maximum elapsed time is 227 days, which is approximately 8 months. The results will be saved for every second time step. Thermal property functions are created under the Key-In Thermal Functions pull-down menu. Choose Thermal Conductivity from the Functions Cascade-In menu and create a new function. The function will be defined using 2 points. Type 1 in the Data Coordinates edit box, then define the temperature and conductivity values for the first point. Click the Copy button to write these values to the list box. Next, define the temperature and conductivity values for the second point. Click the View button to view the 2-point function you have just created. Click the OK button to exit the dialog box and to save the function. You can go back at any time to edit the function. In a geothermal analysis, the amount of water in the soil that is unfrozen depends on the temperature in the soil. Choose Unfrozen Water Content from the Functions Cascading menu. The unfrozen volumetric water content is specified as a number between 0 and 1. A value of 0 means that all the water in the soil is frozen, while a value of 1 means all the water in the soil is unfrozen. This time we're going to create a multipoint function using some of the graph features that are available in all the GeoStudio products. Create 2 points that exist on your function, using the Copy button to accept these values as they have been entered. Next, select the View button to display the unfinished graph of unfrozen water content versus temperature. Click on the Add Point button in the Graph toolbar. You can now add new points to the function by simply moving and clicking the mouse button. You can also adjust the points as necessary using the Modify arrow. Click OK to accept this function. Now the thermal functions need to be assigned to the specific material. Choose Material Properties from the Key-In pull-down menu. For each material, you must specify a thermal conductivity function, an unfrozen water content function, frozen and unfrozen volumetric heat capacities, and a volumetric water content. To assign these values, highlight the default material and use the drop-down lists to assign previously created functions and to define individual values. Click Copy to accept these changes. Click OK to exit the dialog box. Now it's time to draw the soil regions and develop the finite element mesh within TEMP-W. Choose Regions from the Draw menu. The cursor will change to a crosshair. Move the cursor over the sketched lines and click the left mouse button to create region points. Once the polygon region has been closed, a finite element mesh will be automatically generated. In the Regions Property dialog box, click on the Edges tab and fine-tune the mesh. For the first region, secondary nodes are not required. Once the dialog box has been closed, your cursor is still a crosshair, so you can continue to define additional regions. Notice that you can modify the number of elements along an edge by either selecting that edge directly or selecting it in the subdivision list box. The second region should use secondary nodes and have the integration order set equal to 9. Right-click to exit Draw Regions. We don't need to view the region numbers anymore, so choose Preferences from the View pull-down menu. Turn off the point labels and region numbers in addition to the element numbers, and set the node numbers to use a font size of 10. The next step is to apply the boundary conditions. Choose Boundary Conditions from the Draw menu. The temperature at the bottom of the mesh will be 3.1 degrees Celsius. Select Temperature as the type and change the action to be 3.1 degrees. You can either select individual nodes or use the mouse to assign the boundary condition to multiple nodes. The temperature under the ice is maintained at -5 degrees Celsius. Click on the Verify button and TEMP will run a series of checks to see if there are any errors in the problem definition. Now save the file. Before the transient problem can be analyzed, we have to determine the temperature profile that exists in the ground before the ice is installed. These are called initial conditions. Initial conditions are created by running a steady-state analysis with appropriate boundary conditions. To create an initial conditions analysis, save the file under a new name. Change the analysis type under Key-in Analysis Settings to be a steady-state analysis. And change the boundary conditions to reflect a temperature at the ground surface of 3 degrees Celsius. Verify the problem once again and solve the steady-state initial conditions file by clicking on the Solve icon in the Analysis toolbar. Once it's done, reopen the transient analysis and assign the initial conditions file under the Key-in Analysis Settings pull-down menu. Browse to select the external initial conditions file that was just solved. Save the transient analysis again, and click on the Solve icon to start the solve process. Note that the initial conditions file is now being used to establish the initial temperature profile in the ground for the transient analysis. The primary objective of the thermal analysis was to determine the depth of the frozen zone under the ice surface after the ice had been in place for 18 months. You can view the results directly by clicking on the contour icon in the Analysis toolbar. By default, the results for the last time step will be shown, including the location of the freeze-thaw line. To view the results for all the time increments, choose Time Increments from the View menu. Add all the time increments and select OK. These are the freeze-thaw lines that were determined for each time step, and you can use the Contour Label feature to determine which contour line corresponds to which time step. If you want to view contours, you'll need to select a particular time step. Let's look at the last time step only. Choose Preferences from the View menu, and turn off those items that are no longer necessary. To create temperature contours, choose Contours from the Draw pull-down menu. By default, temperature will be contoured and the default values are displayed. Make sure that the contour shading box is selected, then select OK. Each contour interval is shaded a different color, and you can label the contours by using the same contour label icon we used earlier or by selecting contour labels from the Draw menu. Move a cursor over a contour and click the left mouse button to place the label. Labels can be removed by clicking the mouse a second time over an existing label. In Contour, you can spot check results by viewing results at specific nodes or elements. To view the computed results at any node, choose Node Information from the View menu. Click on a node underneath the right edge of the ice surface. The Node Information text box can be manipulated so you can see all the information at once. The parameters computed at the nodes are temperature and boundary flux. The remaining values, such as thermal conductivity and unit flux, are computed at the Gauss regions and projected to the nodes for display purposes. To see the actual computed results at the Gauss regions, choose Element Information from the View menu and click in a Gauss region. It's often helpful to look at a graph of results. To create a graph, choose Graph from the Draw menu. There are many different graphs that can be developed, including a plot of temperature along a vertical section under the ice surface. Select the nodes you want included in the graph and either view the graph directly within TEMP or copy the raw data into a spreadsheet for further analysis. At any time, if you want to go back to define, you can click on the pencil icon in the Analysis toolbar. You can also return to the GeoStudio Start page by clicking on the Start page icon. On the Start page, you have access to some important resource material. You can then return to the current analysis by clicking on the appropriate icon. We have reached the end of this introductory lesson. Not all of the powerful features of TEMP have been used or discussed during the lesson. Specific details about each command are given in the online help and in the supporting documentation for TEMP.